and you consider the information from this pixel alone. So this is called local operation, which means you don't need to bother the rest, information from the surrounding. So this is so-called the local operation. But if the algorithm would consider the information from more than one pixel, which is more than one uh center pixel. The current center or target pixel. So which means that is considered as local. No matter how big or how small is the neighborhood or four connectivity or eight connectivity, that is considered spatial. Spatial operation. So another one would be image transformation. So image transformation, I should use the word geometrical transformation instead. So for geometrical transformation, you're actually transforming to some other location or maybe shear, you know, maybe horizontal flip, vertical flip, and etc. So all those are considered, when you have the word geometrical, you're actually concerning about the shape, the size, um, anything about the geometrical arrangement of the object. Okay, so that is so-called the geometrical operations. And then later on, we have image transformation. So in terms of image transformation, we are referring to transform from one domain to another domain. So what would be the domain? Um, in in the image, we have spatial domain, frequency domain. In audio, we have time domain and etc. Okay, so when you transfer from, some the information from one domain to another domain, you are not actually losing the information from the previous domain. Just that it is not in the same dimension you are at this moment. Okay, so for example, if transferring the spatial domain to a frequency domain, it doesn't mean that all the spatial domain information is lost already. Just that it is not present at this moment. Okay. For example, you break down the RGB, maybe you convert it to grayscale. This is not a good example. Yeah. Okay. You are actually, transferring to one and you're displacing something else. But nonetheless, the original information is still encrypted within the images. So you did not lose any information. Just that in the current domain, some of the information is being highlighted, but some is not. So that is the reason why. Like, okay. So, but nonetheless, we it's still the same thing that we need to in which we need to consider what is the application. If let's say the current application is one, you wish to compress, remove some of the high frequency information, so frequency domain would be the best lah. Okay, partial domain might not be the best because you don't really know which information is important to you. But why? But why most of the time when we do image processing, we are actually processing in terms of spatial domain. The reason why is that we, I mean, we are actually human centered lah. For example, I want to get black color images, or I want to segment the hair. Hair is usually appear in black color, right? So we will segment, maybe using color thresholding to segment the the black color hair alone or the black color object alone. But why we did not use the frequency domain and etc. Sometimes it's because you don't really know in when you transfer the input image to a frequency domain, which part of the frequency domain is representing the hair. That is the reason why we never explore to that part. So from time to time, we are quite encouraging everyone to explore this domain and what information is being represented in this domain. Because when you arrange the data, sometimes when you arrange the data, maybe in spatial domain, you might have the data overlapping in some portion. For example, this portion is overlapping. But when you separate in maybe optical density or maybe the frequency domain or whatsoever other dimension, you might see the data can be well separated. In fact, if you have this kind of data, you would have cluster A and cluster B. Maybe I use cluster one and two. Cluster one and cluster two. But the accuracy usually would be a bit low lah. That is because this uh, data is overlapping here. Okay, but when you transfer to another domain, perhaps you have a very clear cut by using some of the common classifier, maybe SVM, you can get a better accuracy. So that is why um, in sometimes to study the behavior of the data or study the characteristic of the data is important. But nonetheless, when you are using deep learning, perhaps you no need to study this step, right? Because you input everything, right? Um, to some extent, I would think this is part of the drawback of using deep learning because deep learning model is becoming more and more clever. And are we being more and more clever? I somehow I'm not really sure because we train the deep learning model. So let's say you get a very high accuracy at the end of the training. Then if I ask which features is representing that, representing this object, can you understand? Can you explain to me? Somehow it's hard lah. But in the new explainable deep learning model, I think it's possible. But nonetheless, that is still very new. Yeah, because in most of the application, um, because maybe I should put it like this. Deep learning model is more towards engineering, but all the engineering works is to apply, is meant to apply in some application. For example, in medical, or maybe in security, or maybe in agriculture. So in let's say you're applying to this field, for example, I take medical as the example. Medical doctor will never understand this one. So how they, if we want them to use our model, we will need to speak their language. So what is their language? Their language is about what is the features. Is the features comply with sort of standard? If not, so how they can trust this deep learning model? So this is the reason, and this is what I can see at the current bottleneck when we develop deep learning. Because when we mention deep learning, it is quite well established. Everyone know all deep learning can achieve good accuracy, high specificity, high sensitivity. But then the question is why not really many people or many real world is using deep learning? This is the question. Okay. So let's back to here. In this chapter, we actually learn about three different. Before we move on to the frequency domain, we are actually learning three different things, which is the DFT, DCT, and DWT. So DFT is the fundamental, not really the fundamental, but the most common Fourier transform we have, which is discrete Fourier transform. And it's actually perform the calculation using the real value and the imaginary value. So whenever you perform the calculation using the imaginary value, you would expect a very, I would say complex calculation. It depends on it is vary or not vary. Okay, but nonetheless, when using the imaginary part, for sure the calculation would be much more complex. Okay, and DCT is the core of the JPEG, and DWT is the core of JPEG 2000. So DCT is simpler than DFT. The reason is that in the calculation or the computation of DCT, you only need the real part without the imaginary part. So by by excluding the imaginary part, basically the entire calculation will be simpler, lah. Okay, you have a bunch of words, a bunch of integer, do your max, and yeah, everything will be simpler. And for DWT, you have the difference between DCT and DFT would be DCT require only the real value, DFT real and imaginary. DWT, in contrary with these two, is that DWT consists of the spatial and also the frequency domain information. So when you have both of this information, I would say you have a richer information there. A bigger information bank. So you can explore the information in terms of spatial and explore the information in terms of frequency. So basically, when you have more data in, you would expect the algorithm would give you a better sort of maybe quality. But for this one, it's in terms of quality lah. Okay. So this is the core that you need to know here lah. And the rest will be the fundamental. For example, this one. So you have a spatial frequency. This figure is referring to the I would say sort of threshold of the eye, whereby at this region, our eye is less likely to be sensitive. I mean, sensitive to this kind of information. So you have a high contrast, low contrast, and low spatial frequency, high spatial frequency. So this is the region that human eye is much more sensitive to. So in JPEG compression, the idea is that everything which fall within this region is tend to be removed. Okay, this is the common idea in JPEG compression, and I believe not only JPEG but also applicable. Of course, not the same graph, but the same theory is applicable to audio and also video processing. That is because in multimedia, the core or the main character always human being. So we are trying to do everything by exploring the perception or the psychoacoustic of the human. Okay. So the image in the natural world have regions slowly changing color. This is also one of the motivative lah, because it's unlikely to have a image with a lot of, I mean, a very sharp change in terms of the intensity. When even though you snap something very fuzzy, it's very unlikely to have something like this one. That is because in the nature, I mean, all the images from nature, it tends to have a very smooth transition from I mean, if within an object lah, okay. If let's say you have different object arranged, for example, you have a basket and different items inside the basket, so of course there will be a change of intensity. But nonetheless, the change of intensity within one single object is unlikely to be very fuzzy. It's unlikely. So if let's say your input image, the entire input image is very fuzzy. Basically, even though this is an natural image or real image, we would classify or consider it as sort of noise. Okay, so noise is not really after the assignment and the lab. I believe you all quite well versed in terms of noise. So you have different kind of noise, Gaussian, sprinkle, impulse, and etc. So all this kind of noise is tend to be um, introduced. Of course, in real world, the noise is unlikely to be introduced by human. But for an exception, you want to corrupt the image. Else, it is usually introduced by the amplifier by when you convert from one format to another format, when you're sending your file through different bandwidth. So perhaps this will introduce noise to your input image. For example, the Gaussian noise is a very typical noise that would be quite common, especially for electronic device like MRI, CT. Those would be very common. Okay, because and not only this one, even though in audio it's the same. When you have different, I mean, if you have amplifier to amplify the audio file and etc., all those amplifier your mic would introduce noise inside the signal. Okay, so that is how come I mean the source of this noise, and usually the source of the noise is very random lah. We don't even know what is the rate of the noise and what is the source of the noise. Okay, so this would be the spatial domain, and this is the frequency domain. So um, this is one of the image uh, to shows that the high frequency region and low frequency region. So I've been explained this one last time. So basically the low frequency would be concentrated in the center. And of course there is no clear cut over here. Okay, this is high frequency, this is low frequency. There's no clear cut. For example, you have a continuous x and y axis, whereby the x-axis is the height of this student, 0 to maybe 200. So there is no clear cut that, oh, at which level it is considered as tall, at which level is considered short. That is because this is a continuous graph. Okay, if let's say you want to have a threshold, is okay lah, but up to you to put that. But for this one, it's the same. This is a continuous data whereby you don't have, I mean, you don't really have a solid region that this is low frequency and this is high frequency. So but nonetheless, just to let you know, we have two extremes here, and the extreme is the center, and somewhat the other extreme would be the boundary of the image. So the center would be concentrated with the low frequency information, and the boundary is concentrated with high frequency information. So so when you tend to remove this one, I mean remove the items, when you tend to remove or mask out the information of the high frequency I mean the region of the high frequency information, you would get you will still able to get the original image, but of course with degraded details, texture, and etc. That is because all the texture, details, and yeah, all these are considered as high frequency information. So it is unlikely to have a upload image which is very HD lah. Okay, but in contrary, if you mask out the center region and only I mean, remain the uh, region of the bound of the region which is near to the boundary of the image in terms of frequency domain, you would get something like this, whereby you have the edges, the high frequency information, and etc. The edges, the texture, the fine texture, and etc. So, but nonetheless, by looking at this image, it's unlikely for you to know what it is. Okay, so in terms of JPEG compression, we did not really remove all, but we removed part of the high frequency information because we would expect a degradation in image quality, but we don't expect to have a very low quality. But of course, this is controlled by the compression factor lah. Okay, if the compression factor is higher, so you would expect, um, okay, if the compression factor is if the compression factor is very high, you would expect to get a blur image right after the compression. So can I know, is the darker region here growing upwards or inward? Inward, when the compression factor is very high. Smaller meh? When you have a high compression factor, which means you would have a very blur image, right? So during the DCT compressions, during the DCT, you would expect this circle to be expanding outwards or inward. Inward. Inward, which means more is being. One moment, let me think. You're referring to this masking or this masking? A or B? Yeah, A is correct. Okay, because I'm talking B. Okay, A is correct. So which means now when you are have a higher compressions, the output of the image is tend to be more blur. So when it is more blur, which means, yeah, correct lah. Which means you retain lesser and lesser the low frequency information. Which means you expect something like this one. For example, A is the original size lah. B is the size of this red color circle. So you expect B is something with higher compression ratio, but A is lesser, something like that. Okay. Because when you are masking more, you can correlate with the quantization table lah. So you have table, right? So towards this region is low frequency, towards this region is high frequency. So if you have a higher conversion rate, the from the table, the value at this region would be higher, and this region would be lower. Okay, so this is you have to correlate like everything, something like that one. Okay, I hope I mean whatever you learn, don't just solely you know A is A, B is B, but correlate A and B. Okay, because the question will never ask you A and B. Okay, the question will ask you how A and B correlate and what is the relationship between A when B is decreased, something like that. Okay, never stuck yourself in that situation where you only know A and only know B when it is being asked separately. Okay, so this is sort of energy bar. So you have actually energy bar is nothing so special. It is just I would say it is just a technique to illustrate the result. Okay, it is just a technique to illustrate the result. If let's say you all are going to write paper, I mean write any technical paper, it's good for you to explore different kind of method to I mean to present your result. Okay, that is because mm, it's very to some extent it's very boring to present your result just using accuracy. Yeah, accuracy 90%, so something like that. So you have different metrics to illustrate, and always remember when you are using any figure to illustrate the data, make sure the figure serve the purpose. What is meant by the figure serve the purpose is that if let's say you want to show the train, make sure you use a line graph. You want to show, for example, in some thesis, they tend to write multimedia, da 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 da, and then multimedia bracket figure one, and then the figure one is actually a bunch of words, like the matrix. Uh, uh, I mean, how figure one serve the purpose as a figure. Okay, but anyhow, this is about technical writing. All the figure you put inside your the thesis or technical writing, make sure it serves the meaning. If not, you just remove it. Okay. So the energy bar is actually I mean the main purpose of the energy bar is to show which part of the image or which part of the figure has the high energy and has the low energy. In image processing, I think yeah, engineering we did use that, but mostly this is being used in biology lah, because we want to show the gene, the chromosome copy. So you have a T, X, and Y axis, and you have a table with different energy bar, something like that. So, but that one is applied biology. Okay. Um, Nonetheless, this is just to illustrate whereby the center here or the red color shows higher energy. Higher energy, which mean when you have, I mean, when the region of this region, I mean, with high energy, is that this image has smooth transition of fuzzy data. Let me rephrase. If this is the frequency domain. If let's say you have high energy at the center here, can I know the input image, is it with smooth transition or corrupted with noise? Smooth or noise? Smooth, okay. Uh, why it is smoother? Because you have high energy here. Okay, if let's say because or you don't really, I mean, you don't get confused by this image that you have, wow, very big area here, but this is just a very small area. So I think this might be balanced between noise and the smooth transition is wrong, because in terms of this image, we are actually looking in the energy regardless to the area. Okay, so because all the area here is referring to a particular transition, but not the amount of transition. So since you have a red color and the yellow color, which is high and maybe moderate high, most part of the center here. So which means I mean, the input image is tend to have a smooth transition rather than a fuzzy image. But if let's say I mean, in opposite, you have a red color, at the boundary here, so you would expect this image is a fuzzy or corrupted by noise, something like that. Okay, so learn how to correlate. Okay, DCT. DCT is the core of the JPEG compression, and okay. The output of the DCT is known as DCT coefficients, sensitive to low frequency. Okay. Um, Human eye is sensitive to low frequency information, where the low frequency information is referring to all the transition, smooth transition. Okay. High frequency information is that you have a immediate or very um small, I mean high rate of change. For example, 100, 200, 300, and then 100, and then 0. This is so-called high transition. But nonetheless, um, the high or low transition is only, you can only derive this by comparison. Okay, if let's say this is 100, 200, 300, of course you don't have 300, maybe 250 and so on. So because the range of the pixel is quite small, 0 to 255. So a big transition would be easily identified. If let's say you have 0, 255, 0, 255, 0, 255, for example, then that one is sort of the checker box. Okay. So this is okay. The reason why the DCD coefficient is being processed in 8 times 8 or sometimes 16 times 16 is that this is decided by the JPEG, one of the reasons. But the motivation behind this one is that 8 times 8 has the best trade-off between the quality and also the time. Okay. Um, Although we know, I mean, I would encourage the student to know not only the 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 information, something like this one. For example, DCD coefficient is set by 8 times x or 16 times 16. Although you can answer me that this is decided by JPEG, something like that, but I would hope you all know what is the motivation behind this one. For example, we cannot ride the motor without the helmet. I know it is written in the law that is enforced by Malaysian law, but what is the motivation behind that? Something like that. Okay. If let's say you can do something with the same result, but did not comply with that, I think it's still okay. But please do not against the root law. Nonetheless, if you have, if you can propose another method, but you did not comply with 8 times 8, no, 16 by 16, but you can get a better trade-off in terms of time and quality, I would say that that one can be used, something like that. So that is the reason why I would encourage you all, please don't just know I mean, the surface. You have to know the motivation behind an action. That is yeah, that is very important in engineering. Because when you want to do some amendment or improvement, only that part you can amend. If you don't know the motivation, it's very difficult for you to amend or integrate any other new solutions. Okay, so this is the quantization. Let me see. Oh, this is not the quantization table, but this is just the DCT coefficient, and the first value here. I mean, the value towards the top left would be low frequency, and the frequency I mean located at the bottom right would be high frequency. Okay, so again, there is no clear cutoff. I mean, you can put any cutoff, but nonetheless, towards this extreme would be high frequency, and towards this extreme would be low frequency. But the first value here usually, uh, most of the time, I would say, would be higher in terms of value. Okay, and we always call this one as DC. The rest is AC. Okay, so I think I will not explain this one. Nonetheless, it's good for you all to know this one. Okay. I mean, how is this shading? No matter in horizontal and vertical, how is this being formalized? Is that the value on top here, the value on top here would reflect a white color, and then this is a black color, and then this is the something transition between white and black, which is somewhere around gray color lah. Okay, so and when you have this wave, this is bright, dark, bright, or white, black, black, white lah. Okay, so that is why you get different strip. Okay, and when you sum out these two sinusoidal waves sum out, you will get another wave. For example, one plus negative 0.5, you something like that. Just do the summation and you will get the value of this shading here. Okay. Although in examination we will not ask you about this shading lah. Okay, we'll not ask you about this shading, but I think it's important because this shading or the all these sinusoidal wave is the basic in terms of these FT, DCT, and DWT. So it's important for you to at least know why it is. Okay. Mm, the reason why we Uh, since the JPEG compression is performed by using 8x8 pixel block, um, if you have a very high compression ratio, you would expect to see something blocky. The something blocky is that when you partition this into 8x8 pixel block, after you perform the DCT conversion and etc., the individual block might look with a great difference with the adjacent block. So this is the reason why you can see sort of a blocky field, which is also remark a very low resolutions. Okay, that is the blocky field is actually come from the 8x8 lah. If you are using 16x16, so you expect the box is bigger lah. Okay, so DWT is sort of so-called better lah, better than DFT and DCT. The reason is that DWT you have both spatial and frequency informations. Okay, you have both spatial and frequency information. So since you have rich information, you would expect to have a better quality when you perform the compression. So Fourier transform has a drawback of dealing with just frequency domain. The temporal details are not available, and the wavelet transform combine the filter bank technology and address this weakness. So a wavelet is a ripple signal meeting certain characteristic, and wavelet is actually little wave, I mean small change in terms of wave, a function that are concentrated in the time as well as frequency around a certain point. So it is used as a basic transformation, just like the sine and cosine, and used in the Fourier transform. So this is when we illustrate the Fourier, DWT lah. Okay, but I will not go into deep on this one. But nonetheless, you can actually see this is actually correlated to this one. Okay, so when you have uh lower frequency, so the streak will be far apart lah. Okay, when you have high frequency here, so the streak will be decomposed and break down. Okay, so Fourier transform is a superposition of sine and cosine with different amplitude and frequency. In other words, the wavelet transform is a superposition of wavelet with a different translation and dilation. To be frank, if you are very strong in mathematics, you can easily resolve image processing issue. To be frank, if you are very good in mathematics, but nonetheless, the cruelty of the world is that although I have some friends with a PhD in mathematics, but it's difficult to find a job. PhD in mathematics is very awesome to me. Seriously, I have because previously I have some especially mathematical equations I can't really understand. I will go and ask them. And many uh very odd symbol to me. They are very well versed in that. But when we comes to getting a job, no matter in industry or as a lecturer, it's quite difficult for them to get because the world is more emphasis on applications, and engineering is more the application. So that is the cruelty. But nonetheless, when you look back at the Nobel Prize, all those usually they are from mathematicians. Okay, so yeah. So Fourier transform is the superposition of sine and cosine with amplitude and with different amplitude and frequency. In other words, the wavelet transform is the superposition of wavelets, different translation and dilation. So unlike DFT, the DWT, in fact, DWT refer not just a single transform, but a set of transformation, each with a different set of wavelet basic function. So basically, you have different filter bank, which is L is a low pass filter. L is low pass, H is high pass. So LL, which means you have two low pass, HL you have one high followed by low, and the sequence is from left to right. Okay. Again, please do not memorize. Please do not strictly memorize this one because it can be rearranged. It can be rearranged. But the idea is that you have to know when you apply low pass filter, what frequency can pass through. Okay, when you apply high pass filter, what frequency can pass through, and you when you put LL in in conjunctions, so what would be the output? Okay, please do not strictly memorize this one because something like this would be easy, very easy for you to confuse. Okay, as well, especially when the question reshuffle, so it's very easy for you to confuse. So this is the original image. So you have a low pass filter. After you low pass filter, which means only low frequency can pass through, and high frequency will be removed. Okay, so low pass. So after you remove, so you have a horizontal approximation. Approximation is usually referring to low frequency because approximation is you will expect something approximate, like for example, uh, uh, approximation of a step wave. So you will have something like this to approximate okay, but not exactly. Okay, so all the details will be in high frequency. So after you apply the low pass, which means low frequency can pass through. So which means you have only the low the low the low frequency information, which is the approximation information. Okay, in terms of horizontal. And in opposite, you have a high frequency information or so-called the details. And then you apply again the low pass filter. So you have the both horizontal and vertical approximation. And if you apply the high pass filter, you will have the vertical details and so on and so forth. Okay. So this is how you get how actually wavelet transform is being applied and works. Okay. So basically, I believe this one you all at least know lah. That is because no matter in audio processing, psychoacoustic model, the encoder decoder is always just inverse function of the another one. Okay, for example, you have original image, so you apply the low pass, subsampling and extension, you get all this subsample, and then in order to reverse this, basically you just reverse the entire algorithm. That's all. Okay, even though in the audio processing, the encoder and decoder is the same. But the encoder I would be always, of course, not applicable to all, but for audio processing, the encoder is much more, usually is much more complex than the decoder. In terms of, let me think, what else got encoder, decoder? I think in our sleepers, only audio processing got encoder and decoder. Yeah, only audio processing. So in terms of for audio processing, the encoder would be always much more complex than the decoder. And the encoder would be we have three different layers, right? Layer one, two, and three. And for layer one would be simplest, and then followed by layer two and layer three. So with three, all these different layer, different masking is being considered. Okay. So nonetheless, the algorithm here you can try, and this is just a way to show the result. But nonetheless, why the result? LL2, LH2, HL2, LH2, and also HH2 is being put in this box is that this is the approximation of the image. And this all these three box show different detail image in different I mean diagonal, horizontal, vertical. But for this one, it's actually approximation of the original image. So that is the reason why we put it here lah. Okay. Nonetheless, for FIP should be no issue lah. Because for FIP we don't really request for um, uh, sophisticated justification. We don't really request for that one. But nonetheless, I think you all passed through I mean, have undergone your Viva, right? So basically, the main thing people would ask would be the objective. How do you achieve the objective? If you can achieve the objective, usually the FIP no issue lah. Okay. If you cannot achieve the objective, then should be a big problem lah. Okay. So all these are just algorithm, okay, and this is the DWT is the core or the heart of the JPEG 2000 lah. Okay, we will explain this one in the next chapter. Okay, any question before I mean for this chapter specifically? No, okay, if none, then we take 5 and then we continue with chapter 6. Right, right, okay. Yeah, during the tutorial, I think I asked Yu Yang about this one, and the calculation stopped here. So okay, so I think he is correct, and the calculation should stop here, whereby no need to divide by 2 lah. Okay, the reason is that state the Nyquist frequency for the following digital sample interval. So this 50 microsecond and the 0.01 microsecond is referring to digital sample interval. So when we want to the Nyquist theorem is applied when you want to convert you want to perform sampling from an analog signal. Okay, so this should be FM should be the analog signal, the input analog signal. Okay, so say you are using 50 microsecond. So this is the equation, yes. This is a sampling frequency, which is the Nyquist frequency. Because the Nyquist frequency, the definition of the Nyquist frequency should be 2 times the amount, the maximum frequency, right, or the upper boundary minus by lower boundary, right. So this is either the maximum frequency of the analog, or it should be the upper boundary of the analog frequency minus by the lower boundary of the analog frequency. So 2 multiply this one equivalent to the Nyquist frequency. Okay, so the answer here should stop here. Okay, which is 20k lah, but not divided by 2. Because after you divide by 2, you're actually getting the analog signal. Okay, the original analog signal would be approximate this one. Okay, so in order to get the Nyquist frequency, you should be FS instead of FM. Okay, so the question should be stop. Answer should be stop here lah. Okay, very simple this one. Okay, I will upload the tutorial later on lah. But for the first questions, we are discussing this question as well. Is because if a set of ear protector reduce noise level by 30 dB, how much do they reduce the intensity in power? So reduce by 30 dB. Did you all put the negative sign here inside your calculation? Because when you put negative sign here, the value is different a lot. Because without the negative, you will get this value, but with the negative, you will get negative 15. Basically, same as this one, just that negative 15 here. Okay. I'm still thinking about this one because I am not because the logic of this calculation is that the question say that if a set of ear protector reduce noise by 30 dB, right? So basically I just calculate the 30 dB lah, ignoring the sign positive and negative. But after the calculations, I say that the declaration of the answer say that it is reduced by 1 multiplied by 10 power of negative 9. So this is the logic behind the calculation here lah. So any of you are using negative sign here to perform the calculations? Maybe I can listen some of the opinions from you all. Anyone from online? You can put it in the chat box. It's okay. Have you put the negative sign here? I mean, when you do the calculation, this is tutorial 7. Question 1 tutorial 7. No, ayo, okay lah. I will reply you all this one later on. Okay. Because I'm still thinking the value here should be negative 15. I mean, before without negative here lah. Okay. For this question, I will reply you all later on. For this one, I will amend and upload in the upload as a notifications in the Google Classroom. Okay. So, all right. Any questions? None. Okay. Okay. Wow. Okay. Bear with this first, because I think the projector something wrong. But nonetheless, thank you for the answer, and I'm not always correct, to be frank. Okay. So, if you found that some notes is a bit odd, of course you can raise this to me, but you bring something else to debate lah. Okay. Don't just simply say this is wrong or something like that. Okay. Basically, if you tell me this is wrong, then I won't entertain you lah. You bring with some evidence, so yeah, we can come to discussion. I believe not all the no one is perfect. To be frank, I make mistake. Okay, and thank you for that. I'm really happy with the answer. Okay, because it's remind me as well. Okay, thank you. Okay, let's continue. Image compression. So basically, the core of this chapter is that we are discussing the JPEG conversion. Okay, JPEG conversion is important. So before we proceed to JPEG conversion, we have to know um, the principle. I mean, the reason why we need to perform compressions, no matter in video, audio, and also image. The reason only two. Of course, you can break down more and more details. But the core reason is that we have a limited data repository, or we have a limited so-called the storage. The another thing is that we have a limited bandwidth. So if let's say you want to store one or two drama or one or two movie is okay, but later on if you want to store more and more up to million images, so it is not so possible, and the way you need to manage the images is very very tedious. So when the image I mean when you have an image and you or whatsoever data and you store in your local drive, that is so called multimedia storage. But when you have more than manageable data stored in local, it is called as big data. Big data is another term that is emerging recently. I think there's some journals with the title Journal of Big Data. So big data is that the amount of data is very, very, very big until you cannot manage using software or internet platform, so-called big data. Okay, and the big data is highly correlate to AI or deep learning, I would say. Not only AI, or not only deep learning, but general AI as a whole. So the big data, because in everyday life, we are keep on producing numerous data maybe whatever we click, whatever we use, and etc. Of course, in and one of the example is healthcare lah. For example, I am going to examine for COVID maybe. So when I go and check in and etc., have my imaging, X-ray and etc. All these are considered data. And how this this is only one day, oh, and then later on after another day you come here, another checkup, another diagnosis, another paper. All this being correlated and become your medical healthcare history. Okay, so that is the reason when you want to diagnose something else, people will ask, do you have any medical history? Medical history, last time is something like written in a report form, but now it is accessed, like a cloud or something like a cloud. And the NIH, National Institute of Health, which is from America, lah, okay, uh, they are actually launching a program called All of Us. Okay, so this project is actually trying to archive more than 1 million and more healthcare records, so that to use this All of Us data to train the deep learning model. So this is what America is launching. I think it's launched just recently. All of Us this program, and that aims to get 1 million and more lah, data record across the world for the next few years. Okay, so this is how big data is being used to predict things, prognostic and etc. Okay, so back to here, we in terms of data compression, we have lossy and lossless. Lossy, which means you cannot convert back lah. Lossless, you can convert back. Okay, so, but the difference between lossy and lossless is that usually the lossy compression factor will be higher, lossless will be smaller. Okay, but nonetheless, lossless you can convert back to original one, but lossy cannot. Okay, so JPEG is DCT is the core of JPEG, and DWT is the core of JPEG 2000. JPEG 2000 you have two different lossy and lossless, but for JPEG only lossy. Okay, so basically our computer don't have JPEG 2000 extension. I think last time I've been search the extension for JPEG 2000 is different. Is different and not JPG, not JPEG, not something like that. Okay, so basically our uh, computer, I mean normal computer is not equipped with the JPEG 2000 conversions. The reason is that uh, the software or the conversion algorithm is not always we select the one which is popular, but sometimes we select something which is well accepted by the public. Okay, so this is one of the cliche example I would say JPEG compression and JPEG 2000 compression, because in terms of quality of compression, JPEG 2000 is actually perform better than JPEG. But nonetheless, JPEG compression receive much more attention from the public. Okay, so this is the reason why most of the IT or the PC manufacturer use they use the word they use the words sorry, they use the extension of JPEG compression instead of JPEG 2000 compression. Okay, okay. Of course, this list you don't need to memorize, but you have to know when you need to divide by 8, when you need to divide by 1024. Okay. Always, I mean, this is a very simple calculations, but somehow you need to uh, practice a bit lah. When you convert bit to byte, so you need to divide by 8, and then you divide by 1024, but not 1000, even though you're converting to kilobyte. That is because the calculation in bytes and normal meter, kilometer is different. So make sure you are clear on this one. And again, in the final exam, no formula or no extra attachment is given. So everything is in the question paper, else you have to memorize it. Okay. This is just an example of information. We move to JPEG conversions. Okay, JPEG compression is important. Okay, which gender conversion is important. So do study this one. Do understand what is uh to me, JPEG compression consists of mm, many chapter because in order to know the entire flow of the JPEG compression, you actually need to combine knowledge from several chapters. Okay, not I mean, please do not just solely think that JPEG is JPEG. When it's come to JPEG, you have to know why CBCR, and you should know why CBCR should be around chapter 2 or 3, which is color image. Okay, and subsampling, which is in video processing, and DCT, which is from chapter 5, and yeah, the rest should be in this chapter. Okay, so it is not something just from this chapter because I mean, if let's say the JPEG conversion is the first chapter, so basically it's quite difficult to understand because you never learn about the image, color image, you never know about the subsampling, you never know about the DCT, DFT, and DWT. So it's difficult. Okay, so basically JPEG is not only referring to chapter 6 alone, but correlate with other chapter. Okay, so input image. So first of all, convert to YCBCR. Why need to convert to YCBCR? Why do not use or just simply uh, process by using RGB? This is interesting question. So you have to know. I think I have been answered this question. Is that the RGB is you cannot just simply, because the next step is subsampling. The reason why we do not just okay, the reason why we did not use RGB is that any algorithm that you perform in RG or B channel, you have to perform equally to all 3 channel. And you cannot simply subsampling either of the channel because later on you will have syntax to merge it up together. And why we do not use grayscale? Grayscale is only 8-bit. The reason is that I think you already answered these questions in your assignment. Is that when you perform the edge detection, or I think it's lab, when you perform the edge detection, when you compare the input image, separate into 3 different channel, perform edge detection and merge together. When you compare this output to simply just convert the input image to grayscale and perform edge detection, when you compare these 2 images, you will found that the edge detection performed in each of the channel and then combined together is actually has great details when you compare to the edge detection alone in the grayscale of the original input image. Okay, so this is the different, and this is also the reason why we don't just simply convert the input image to grayscale, rather we convert to YCBCR. Okay, so this is the reason that, and we perform subsampling, which is 4:0. So when you have 4:0, which means your compression ratio is around 75%, because you only retain 2 channel, not really channel, but 2 color modes in terms of A and 0 color mode in terms of B. So the rest of it, you have to know what is the difference. So you have only two. You have only two. So this is A and B, right? A and B. So this is the whole is the J, right? So you have only two, which is I think it's the first one and this one, right? Not really remember, okay. Either this one or this one lah. Okay. Or either this one or this one. Okay. So basically, you share the same color. Uh, oh, you will share the same color across these four, and another same color across these four. Okay, so this is how you perform the subsampling. So after you perform the subsampling, basically you remove up to 75% of the uh, storage in terms of CB and CR. Okay, but Y we remain unchanged. So we use Y and subject to another process. Why we perform subsampling in terms of CB/CR is that our eye is not so sensitive towards chroma channel. Chroma is the color channel, and the Y is the brightness. Okay, so we are much more sensitive to brightness. Although although the Y channel here looks very similar to grayscale, but actually the details, this Y channel hole is much more greater than the grayscale. Okay. Do not judge the image just simply by our human interventions. You might have error. So later on, we convert it to 8 times 8 pixel group, and 8 times pixel group. The reason is that this obey the Nyquist theorem. Is that sorry, this is not obey the Nyquist theorem. This is just simply JPEG say that this has a better trade-off between the quality and the time taken. Okay, so later on you perform block shifting. Block shifting, yes, you obey the Nyquist theorem because you minus by the mid value which is 128. Okay, simply just 256 divided by 2 like 128. Okay, so you're actually shifting the blocks to obey the sinusoidal wave. Okay, shifting it downward. So the maximum would be 128, the minimum would be negative 128 lah. Okay. So later on perform the DCT. After you perform the DCT, you will get the DCT coefficient. So from here, you will need to perform the quantization. So the quantization here is actually the quantization table is provided by the JPEG, and the quantization table is one moment, quantization table. And the quantization table will be provided lah. If let's say it is it will be provided. Simply you just need to divide by the number from this lah. Okay. Say this is the quantization table. So 512 divided by 16 and get this one. So um if the table, I mean, if the quantization table is higher in terms of the value, the value sheet is higher, which means the output will be smaller, lah, which means the conversion ratio will be greater. Okay, and during this block shifting step, you would get a negative value. You will get a negative value, something like that. Okay, so do not surprise when you have a negative value. Okay, and that is the only step lah. You will get a negative value. So after perform the quantization, so you have two different value, which is AC and the rest is DC. Sorry, this is DC, the rest is AC. Okay, so this is DC, the rest is the AC. So you have a different processing using DC, I mean for DC value, and different processing using AC value. So the DC value you are subject to DPCM, and the AC value you are subjected to zigzag ordering and also RLE. Okay, so we continue. Sorry for that. The DC value is subject to DPCM, and the AC value is subjected to zigzag ordering and RLE. So you should know how to do the DPCM lah, and also the RLE. Although there is a bit difference, but more or less the idea is the same. Okay, the DPCM is that you have this series 150, 155, 149, 152, and so on and so forth, and then you actually only need to keep the first value 150, and then the rest you code the difference. Okay, 155 minus by 150, you will get 5. So 5. And then 159 minus by 1455, you get negative 6, and so on and so forth. Okay, so basically, when we code only the differences, we need smaller space to we need a smaller space to store this kind of value. So the same idea is being used in in video processing. So we have I frame, P frame, and B frame, right? So I frame is the reference frame where everything, I mean, you can see although it is not really the same thing, but you can see the iframe as the first DC value, whereby it is independent. Okay, so the P frame and B frame is something from this iframe. So basically, you will put the differences. This is the iframe, and for P frame and B frame, you might put the arrow only, which means the differences are not the arrow, the differences. So if let's say if in this case the size required to store the value of P and B frame and others frame, I mean more P and more B, it is actually taking up smaller space lah. Okay, so the idea is being used by the JPEG and also being used in video processing. So the DPCM is referring to this one lah. So the AC value is the rest of the value. We are performing zigzag ordering. So zigzag ordering is something like this one. So starting from here, so zigzag ordering is starting from here. Basically, this is the patterns. Okay. Make sure you don't do the other way around. Which means you don't start here. Okay. If you start here, then bye bye. Okay. That's all I can say. Yeah. Although sometimes I know it is just careless, but the answer is like that, so I have to give you a cross. Okay, so if you go to the wrong direction, though, that's all. Okay, your mark stop here. Okay, because the rest would be all incorrect. Okay, so after the zigzag ordering, you would get this one. So for example, this is an example. So the zigzag ordering should be something like this one. And so on and so forth. Okay, until the last one. So you will get something like this 32, 6, -1, -1, and 0, so on and so forth. So, yeah. So run length encoding RLE for AC coefficient. Nonetheless, RLE is part of the encoding method. You have much more different kind of encoding method. But in JPEG, we are using this one. But please do not restrict yourself that actually only run length encoding is available, because we have different approach for different compression or different processing of data, especially in terms of I mean storing the data in terms of computer science. So ILE is part of it. Okay. So the run length encoding is then applied on the 64 vector by replacing the value by the run length and the value. Okay. So after you get this, this one is where you get from here. So after you get from here, the first one is the DC value. So I mean in practical, the DC value should be uh stored in the separately with the AC value. So that is why uh, at this part you will still seeing, I mean the DC value is still there 32, but in this part DC value is no longer there because it is being stored in another methods, so-called DPCM So DPCM would have another string to store it, and the AC value will be stored over here. Okay. But nonetheless, when you do the calculation, I mean, when you do the bookings, so you should include this step and then followed by this one. Okay, you can, of course, you can explain separately, but this is just, I mean, this is the step just after you get the this value after you get the quantization value. So for this one, how do you formalize this one? Let me explain this again. So you don't have any zero value, so put a zero. I mean, don't have any zero, skip so-called. So a zero, and the next upcoming value is 6. So 6. And then another bracket. So do you have any zero between -1 and 6? No. So 0. And then put your next upcoming value, which is -1. Do you have any gap, I mean zero gap between the -1 and -1? No, so 0 and -1. So, oh, that is 1 0 here, and the next value is -1. So since there is 1 0, so put 1 here, and the next upcoming value, -1. So for this one, you have 1, 2, and 3. So 3 0 and -1, and 2 0 1, and a lot of 0 until the last one. So 0 and 0. So this also record the last one. Okay. Uh, Please do not mix these two. Because I think some of you may mix these two, whereby you did not give me this one, you give me dot 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 zero, something like that, which is incorrect. Because for this one, I mean, in terms of run length, this is to denote the ending, okay, not this one. Okay, so after that, you have done your DPCM, you have done your zigzag ordering. Zigzag ordering is simply just the zigzag value, so that you get this one. This is the zigzag. After zigzag, this is RLE. Okay, this is this is RLE. Okay, please do not confuse when I ask for RLE, you give me this one instead. Okay, so after that, both of these join together to form the entropy coding. So the entropy coding step would be proceed with the using the 8x8 pixel block. Okay, so in entropy coding, I did not really give you the full table of the Huffman coding, but again, Huffman coding is only part of it, and Huffman is usually used lah. You will see Huffman is quite common when you want to convert the, I mean, in terms of computer science, Huffman coding is very one of the common coding method used. Okay, Huffman coding. So you have Huffman coding, and of course you have Huffman table as well. So the DC coefficient are differentiated differentially coded as size and value. And the code for size can be derived from Huffman table for DC coefficient field size field. If a DC coefficient is 40, the previous coefficient is 48, so the difference is for -8 lah. So which means 40 previous okay, start with 48 first, not this one. So you will not store 40, but you store -8, and so on and so forth. Okay, so therefore it is good as this one. How you get this value? You're actually getting from the table here lah. Okay, so since you have the first one is 48, the second one is -8, so from here you need to find -8, which is this one, -8, and then -8 get your code and get your size. Okay, so obey this one, size and value. So size is 4, and the value is this one, -8. So this is the code which represent -8. So after that, get your size from here, 4. So from 4, you get the code 101. Okay, so then size followed by value, right? So size is 101, 101. The value is 0111. So that is how you get this value. Okay, so do practice lah. Of course, I did not give you a lot of different example, because this is quite, I mean, the full calculations to do the entire algebra is very complex lah. So I did not really give you the full calculations, but nonetheless, you should know how to get, I mean, how actually you get from, -8 until you get this one. Okay, you should know how to get. Okay, so this table, and then entropy coding for AC coefficient. So that is just for the DC coefficient, only one example lah. But of course, if you have more and more append at the behind, for example, 48, -8, maybe -5, -4. So you need to get the big code using the same method lah. Okay. So entropy coding for AC coefficients. AC coefficients are coded as S1, S2 pair. So S1 is the run length size, and S2 is the value. So run length slash size. So the run length is the length of the consecutive zero value, 0 to 15. And the size would be the number of bits needed to code the next non-zero AC coefficient, 0 to A. Okay, in hex. So 00 here, 00 denotes the end of blocks. So basically when the algorithm recognize 00, which is the end of block as of this one, as of this one, so it will stop the entire algorithm. This is also a signal for the image to stop lah. Okay, sorry, for the algorithm to stop. And then S2, the value of the AC coefficient refer to size and value table. So let's look at this one. So this is the example. Um, So first of all, you perform the zigzag first, something like that. So the zigzag order is because 4D is not included, is that so 4D is the DC value. This is for AC only. So you start with 12 lah, 12, 10, 1, -7, 2, 2 zeros, and then followed by -4, 56 0. Okay, so 12, the obtained code is this one. How you get this one? Size and value table. First of all, 12 is somewhere around here. So the value is this one. So the size is 4 and go to the size value. Since you don't have any zero skipping, so 0, 4 lah. Okay, you will get this value. And then you join together this value 1011 and 1100. So you will get this one just for 12. This is just for 12. And then you need to repeat this one for the rest. For example, 10, 1, -7, 20, and -4, and so on and so forth. Okay. So after that, you should get something like this one. And you join together to form the full bit. Okay. Of course, wouldn't the question shouldn't be like this way lah. Won't torture you all like that lah. Okay, don't worry. Basically, just need to. I mean, if you know how to do one question, should be no issue lah. You don't need to do for the whole part. Okay, so yeah, something like that lah. Okay, the question shouldn't be torture you like that. So that is for JPEG. Okay. Nonetheless, the core that we learn in image compression is JPEG only. Of course, we should know about JPEG 2000, but nonetheless, the core function and the entire flow, the detailed flow of JPEG 2000 is not included as part of the syllabus. Okay, but you should know that JPEG 2000 actually have a better performance in contrary with the JPEG. Okay, so the Joint Photographic Expert Group JPEG is under both the international ISO lah and also the ITU-T. So the JPEG committee has defined and published a new standard with this JPEG 2000 to anticipate the needs and requirements of next generation imaginary application. So JPEG 2000 is based on wavelet compression DWT compared with DCT-based compression used in JPEG. So the JPEG 2000 actually has a better compression efficiency, improved subject image quality, and additional functionality compared to JPEG as the region of interest coding. So in particular, JPEG 2000 addressed the following issue, which is low bit rate compression and transmission in noisy environment. So JPEG 2000 can offer excellent subjective quality at bit rate below 0.25, which cannot be achieved by JPEG. Okay, and JPEG 2000 provide improved error resilience for transmission in noisy environments such as wireless network and internet. So comparison between the JPEG compression and JPEG 2000. So this is JPEG compression and this is JPEG 2000. So you can see that the value, I mean, is very, I mean, the quality is very low lah. And somewhat, can you see this gray color and purple color? Especially the purple color is there is two things for you to observe in this image. First is the blocky field. Can you see all these block? I think it's quite obvious, right? So this blocky field is from the compressions of 8x8 pixel group or 16x16 pixel group. But for this color, the original image doesn't have this color. The original image don't have this color. But for this one, why there is, this, what should I call this? The blue, everything is blue, okay. The purple color here, the gray color here. The reason of getting this artifact is because of subsampling. Okay, this is from the subsampling, and the blocky field is from the JPEG compression. Okay, so please do aware of this. I mean, don't just simply blame everything for JPEG alone, because subsampling might has this issue. Okay, especially when you use high compression in terms of subsampling. For example, 420, 411, usually will have this issue like, whereby I mean, because you are sharing the color code, color box, either 411 or 420, you're actually sharing amount different, I mean, a huge range of color. You should have four, right? But now you're sharing the color. So that is why there is artifacts like this one happen. Like this one, this one. In original, you don't have this one. Because because the CB and CR is the channel who control the color. Although our eye is not so sensitive towards this color channel, but it is still, I mean, we are not blind lah. We are not sensitive only, but we still can perceive the color information. Okay, so that is why when you use limited color to represent the full scale of color, you will have this kind of artifact. Okay, so this is due to the um subsampling, and basically this is part of it lah. But this is not so important. Just FYI. Okay. Any question for this chapter? Yes. No. Okay. No. Okay. If none, so that's all for today, I think. And then I will upload the tutorial later on in the Google Classroom. And yeah, I think that's all lah. And we don't have any tutorial this Thursday. Okay, this is odd week. And yeah, let me know next week should we have the class as usual or how lah. Okay. Yeah, that's all for today. Thank you.